All right, let me just quick walk you through a couple of example problems real quick, similar to something you might see in the homework. Exercise 5. Researchers in the Antarctic measure the temperature to be negative 40 degrees Fahrenheit. What is this temperature in Celsius and in Kelvin? So we have negative 40 Fahrenheit, and we needed to go to Celsius, and we needed to go to Kelvin. So I got this equation from your book. So we do 5/9. So we do 5/9 times the temperature in Fahrenheit, which I'm going to plug in negative 40, and subtract 32. You crunch it all out, and we get negative 40 degrees Celsius. But negative 40 is the only temperature where these two scales agree. If it's negative 40 in Fahrenheit, it's negative 40 in Celsius. Then to find it in Kelvin, we're going to plug in whatever temperature we had in Celsius and add 273. So we get 233. In the header of those problems, it said to treat all of these temperatures as exact, so we don't have to worry about sig figs. But if you rounded that to 230, that's fine. Exercise 13. How much heat in kilocalories must be added to 0.5 kilograms of water at room temperature, 20 Celsius, to raise its temperature to 30 Celsius? So here I am on page 117, and I'm going to look up the specific heat for water. I can either choose it in kilocalories, or I can choose it in joules. Well, now that we're getting more towards chemistry, and the problem specifically said that they wanted the answer in kilocalories, we're going to choose the first column here. So the specific heat of water is 1 kilocalorie per kilogram per degree Celsius. And I'm going to use this equation to calculate the specific heat. And oh look, there's the specific heat of water right there. So the heat is going to be equal to the mass times our specific heat, which was 1 kcal per kilogram degree Celsius, times the temperature change, which was 10 degrees Celsius. Then the kilograms would cancel out top to bottom, degrees Celsius cancel out top to bottom, and we end up with 5 kilocalories. All right, for exercise 17, how much heat is necessary to change 500 grams of ice from negative 10 degrees Celsius into water at 20 degrees Celsius? So there's 3 different steps here. First, we have to warm up the ice to the melting temperature. So we have to go from negative 10 to 0. And then once we're at the melting temperature, we have to put in the latent or hidden heat to actually melt it. And then, once it's melted, we put in more heat to heat up the water from 0 Celsius to 20 Celsius. Right. So while we are increasing the temperature of the ice in the water, we can use the equation, we can use the specific heat equation that we just used. But while we are actually doing the melting, we have to use the latent heat equation right here. And since we are doing melting, we will choose LF, the latent heat of fusion. The LV here would be for boiling or condensing. The LF is for freezing or melting. So we have 500 grams, which is going to be 0.5 kilograms. So first, let's warm the ice to 0 Celsius. So our equation is H times the mass of 0.5 kilograms times the specific heat of ice, which I looked up in the table was 0.5 kilocalories over kilogram degree Celsius, times the temperature change, just like we did up here. Here's for melting the ice into water. So this is the latent heat equation. So H would be equal to the mass times LF, the latent heat of fusion. So we have 0.5 kilograms of ice, and it's going to take 80 kilocalories per kilogram in order to make that transition. So this is going to be some extra energy that we'll need. I crossed off kilograms as they cancel. And finally, we have to warm the water to 20 degrees Celsius. So we basically use the same equation again for heating up the material, but now we use the specific heat of water instead of the specific heat of ice. So the heat required to do this is equal to the mass times the specific heat of water, which we get from a table, times the amount of temperature change. And we're going from the melting temperature of 0 to 20 degrees, so it's a 20-degree change. Degrees Celsius cancel out and kilograms cancels out. So we get 2.5 kilocalories from up here. From here we get 40 kilocalories, and from here we get 10 kilocalories. So then the total energy needed from all three of these phases is 52.5 kilocalories. I rounded it to 53. Exercise 19. A sample of neon gas has its volume quadrupled, so 4 times bigger, and its temperature held constant. What will the new pressure be relative to the initial pressure? So like, how does PF compare to PI? So the first thing I'm going to do is kind of write down what I do know, how final and initial compare. So the final volume is equal to 4 times the initial volume. So the final volume is bigger. The final temperature is equal to the initial temperature, whatever that happened to be. All right, and we're trying to figure out the final pressure. So I get this equation out of your book. Your book had subscripts 1 and 2. I used initial and final. I think that makes more sense to me. So final pressure over initial pressure is equal to initial volume over final volume times final temperature over initial temperature. And whenever I'm dealing with the ideal gas law, I like to put in a little subscript K to remind myself that it has to be in Kelvin. Now, the final volume is equal to 4 of the initial volume. We wrote final volume down here, but that's also equal to 4 times the initial. So instead of writing this, we could say 4 times the initial volume. So that's what I did here. I rewrote all of this again, but instead of saying final volume down here, I said 4 times the initial volume. The final temperature is equal to the initial temperature. So instead of saying the final temperature, I could also say the initial temperature because they're equal. I can just substitute it in. So here, instead of saying the final temperature, I said the initial temperature. Then this VI, initial volume, can cancel out. Even though we don't know what it is, it's going to cancel out. If this is 5, that's 5. If this is 7, that's 7. They'll cancel out. And the same with the temperature. They cancel out. So all that's left then is this 4 in the denominator. So then this can go to 1/4. So if I rewrite that out, P final over P initial is equal to 1/4. But I want to get P final all by itself for my answer. I can multiply both sides by PI. And if I multiply a PI to the left side, these cancel out, and I get a PI on the right side, an initial pressure. So the final pressure is 1/4 the initial pressure, or 4 times smaller.